So today's topic for 101 Agronomy, I wanted to talk about the use of silicon in agriculture. So a little bit of my background I think is appropriate here. When I did a PhD at UC Davis in entomology, looking at the interactions of crops and insects and fertility programs, specifically looking at the use of silicate-containing fertilizers and their ability to fortify the plant, fortify cell walls, and what that influence looked like on arthropod populations. Notably, leaf miners was the majority of my work, but also looked at thrips, aphids, mealybugs, a couple other important pests, and an assortment of crops, and had a really interesting time there, kind of figuring out how to use fertilizers and really interesting results. The bottom line was we saw that the addition of silicate-containing fertilizers, in my case potassium silicate is the majority of what we worked with, but also calcium silicate in the form of Mainstay Si from Redox. We also we saw reduced damage from pests as well as reduced pest populations. We had a parallel project also looking at citrus leaf miner that another graduate student did, Dr. Danica Maxwell now, that she did, that saw parallel results that silicate supplementation reduced second generation pests, reduced damage, reduced number of mines, so on and so forth. So both of those were fun projects. So how does that happen, I guess, is what I want to talk about. So why we're hearing more and more in the marketplace about silicon containing fertility inputs and how that works. They've been on the market for a long time. Why do people care more now? What's the importance of it? I hope we can kind of hit on a couple of those topics here as we're driving down the road. So first of all, I guess what is silicon? So silicon's an element on the periodic table. It's a primary primary ingredient, or not ingredient, primary component of all soils on Earth that are all silicate-based soils. One of the challenges, however, is that silicon, it does not weather out of soils very readily, so it tends to be unavailable, bound up in structural mineral structures, and because of that, it can be a limiting factor in some crops. Some crops are notable in their ability to accumulate silicon, such as rice, corn, sugarcane, definitely rice and sugarcane, corn to some extent. And other monocots generally can accumulate silicon at fairly high rates. Rushes and some other non-agriculturally important plants can accumulate silicon at very high rates. Up to 10% of their dry weight could be made out of silicon that they've deposited into special organelles they have that they can deposit silicon in. When you feel a rush and you feel that grittiness, that's silicon. Same thing you think of a rice leaf. It's a very rough leaf. It's silicon. So that's those. Now, dicotyledonous crops, which are the majority of what I deal in, can accumulate silicon as well. There's a notable among dicotyledonous crops for silicon accumulation, or cannabis is one. We also see similar efficacy in strawberries, and even into lettuce and some other of the softer leaved crops that we grow. And so there really is there's the ability of plants to accumulate. Now, the plants have special transporters in the roots that actually can function to pull silicon out of the root and get it through the Casparian strip and all these things. So it is a nutrient. It's classified as a plant beneficial nutrient. Nobody's ever been able to demonstrate classic deficiency symptoms with silicon. Part of that is that it's very hard to remove silicon from a system. Nobody's figured out how to do that. First of all, you try and grow a crop without silicon, it still ends up in the tissue, so nobody's figured out how to get rid of it. The other part of it is that the silicon deficiency that we see is weak cell wall strength. So you still get a plant, it's just a very, very feeble plant that has a lot of just weak cell walls, and so it breaks, it blows over easy, you get soft fruit, it decomposes quickly, it's very susceptible to pests. So all these things I've listed off are really because silicon plays a role in cell wall structure, and so when you have when you're short on silicon, you end up with weak cell walls, and that means you end up with weak plants. So what does the literature say about silicon, I guess? So the literature as a body generally supports that silicon supplementation can improve your leaf toughness, I should say, and most of that is measured by pathogen resistance. So when you have silicon in a system, you see that those plants, when subjected to assay where you infect them with pathogens, they get less pathogens compared to a control. You also see the same thing in the plant's ability to deal with other stress, such as heat stress or drought stress. They tend to stand up longer to drought stress, and then they also tend to have meaning they don't wilt as early, and they also tend to bounce back once they do receive water more quickly when you have more silicon in the tissue. The research has also indicated that there may be some ability of silicon to help increase antioxidant production within the plant and help the plant to deal with there's been a couple papers suggesting that maybe the plants are able to recruit parasitoids and predators more so. That literature is still being sussed out and isn't really well understood at this point, but it nonetheless is kind of an interesting aspect of silicon research. We also have seen, we're going to turn a corner so now you can see the back seat, and silicon has also been very influential in fruit quality, and that's really where it has shown over the past couple of years, has been in fruit quality studies as well as storability and things like that. So we see a lot of results coming through in that, especially in rice. Rice actually is a unique crop, as well as sugarcane, in that they can actually deplete the soil of soluble silicon, so you can end up with an excessively soft crop because it has previous cropping cycles have actually depleted all of the silicon out of the system. So kind of an oddity that those crops get to claim. So that they in many places you can aggressively supplement silicon with industrial byproducts and things like that. That can be helpful. So one of the biggest challenges, I guess, with applying silicon to crops traditionally has been that it comes from industrial byproducts, so it can be a dirty input in that it comes with a lot of heavy metals and other things like that. The most accessible form of silicate in the past has been potassium silicate. It's a liquid, high pH. Big drawbacks there is it's very reactive. The pH is very high, 11 and a half, something like that. If you have it at high concentrations and try to neutralize the solution, you'll end up with water glass or gel, which is very fun to do. I did that at the beginning of my PhD career. Made a jar with a pH meter in there, neutralized it with some acid, came back after lunch, and I had this beautiful jar of gel with a pH meter stuck in it that I'd left there when I went away for lunch. So learn that lesson. But even when it's added into solutions, spray tanks and things like that, if it's not done properly, you can end up with some handling issues and can have some handling challenges because of its reactivity. It'll also react with other ions in solution, making things unavailable, as well as the silicon less available. So can be a challenging input. Now that being said, we've seen lots of efficacy in the past out of potassium silicate. That's what I do my research with, and it can be a very nice way to provide silicon into the system. There's been several other products on the market that have very similar handling attributes, where pHs are very high to keep it in solution, and has have been good. There's also spreadable materials or products that are like calcium silicate that are fairly insoluble and not really used in solution, but are used as amendments, I guess would be the right way to put it. Used as amendments into potting mixes and into soil applied amendments, and those have been widely used. And there's a large body of research of soil amendments from calcium silicate, also an industrial byproduct, or it can be mined out of some specific mines that have some pretty decent solubility. We also see there's a whole lot of other silicates. There's a sodium silicate, there is potassium silicate, there's calcium silicate, there's lithium silicate. You can kind of just go down that column on the periodic table, and and some of those have made it to the market, some of those haven't for obvious reasons. So that's been silicon in agriculture, I guess, for the past several decades. I will say there, so I said silicon. So silicon is the element, silicate is the mineral, and then silicone is one that we hear a lot. Silicone you can think of as more like a plastic. So silicone is what you use to seal your windows as a lubricant in industrial lubricants, things like that. So that's silicone. Silicon that we're putting out for nutritional purposes in agriculture is actually silicic acid, which is the soluble form of silicon as it exists in an aqueous solution in water. So so that is silicon. That's what we're going for. That's the goal. Okay. So from here, I guess I want to talk a little bit about Redox's Mainstay Si, and now Mainstay Si Organic that we brought to the market this last couple weeks here in California, and how those differentiate from themselves from the rest of the marketplace as described. So Mainstay Si is a liquid product. We run it through some unique manufacturing processes where we take calcium silicate and break it apart through manufacturing processes, and then stabilize it with some surfactant technologies. We call it microencapsulation, and then that is stable in the jug to the point where we have calcium and silicon available for the plant. Now, one of the key features of this process is that we do a very complete job at stabilizing that calcium and silicon. So we can actually take Mainstay Si, which is high in calcium and high in silicon, and we can combine it with a product like a phosphite, which is generally extremely reactive with a calcium input, and have a tank stable spray solution that could be applied even through electrostatic application and have high efficacy of both products. So that has given us the ability to get much more access into the agricultural application systems because of that step up in handling capability. So it's been very good. Now, also with that availability factor comes use rate reduction. So our application rates are very low to have that silicon and that calcium be taken up to the plant, because we're having very, very low tie-up on the leaf surface or in the spray tank. So it's been a very nice product for that reason. It does require some agitation, can be a heavy product, and the exciting thing is now that we have a organic version of it, we have a way to apply an available calcium and silicon into organic to really help build cell wall strength, to fortify cell walls, and get a stronger plant that will deal with stress better. Organic production, organic growers have far fewer tools to deal with plant stress, and this is going to be a great way to help just build a stronger plant that will stand up to stress better through just structural stability of adding more calcium and silicon into the system. What else? Both these products available widely on the market, and I think that's kind of the summary. I look forward to questions and comments below. If I missed anything or misspoke, please let me know. Love to share accurate information. So I hope we have a lively discussion in the comments section, and look forward to hearing what other calcium products people are using on the market, what other application points we've seen, specific timings that people feel calcium is very important. Generally, we recommend it early or post with bloom, and then early fruit development, as well as when we have a lot of tissue being developed. So when we have big green flushes, we like to see some extra calcium and silicon in there to help build out that tissue as it's there. So thanks for listening. Thanks for joining me, and looking forward to your comments. Thank you.